everyone, this is Himabindu from the Department of CSIT. So today in this video I would like to explain about the topic called Church-Turing Thesis and Recursive Enumerable and Recursive Language. So what is these topics which related with the Turing machine? So what is this thesis and what is this Recursive Enumerable language and Recursive Enumerable concept? So here, this Church-Turing thesis is also known as a Church hypothesis. So this thesis is also known as Church hypothesis, and which was created by the two persons. Alonzo Church and Alan Turing. So these are the two people which are created this thesis, and everything that can be computed by the Turing machine. So generally the statement which says that the everything, so whatever the digital computers or whatever the models which are related with the computation, so those are all will be calculated, or those are all be computed by the Turing machine. So that is the statement which says, and anything that can be done on existing digital computers. So what we discuss, so digital computers, so which will calculate or whatever the digital calculator is doing, those all are be performed by the Turing machine also. And alternative models are proposed for the mechanical computation, but not them powerful than the Turing machine model. So here, by seeing this alternative models, no other models which are performed for the mechanical or computation, so that those are all also performed by the Turing machine. And here the implementation of an algorithm. Suppose here if you want to implement an algorithm in the Turing machine, so those are primarily matters of organizing the data. If you want to implement or anything will be performed by the Turing machine, first we need to organize the data storage areas, and we need to choose the bookkeeping mechanism. So what is this bookkeeping mechanisms, in the sense what the input what we are taking, where we are placing. So for the regular languages we will place the input values in the tape, if that is a limited tape. And in coming to the pushdown automata, we are replacing all in the stacks. So stacks. And now when coming to the Turing machine, so we need to place in the infinite tape. So these are all the things we need to primarily focus on the three things. So one is organizing the data storage areas and choosing the bookkeeping mechanism. So here, instead of here bookkeeping mechanism, so suppose if you are reading 0, we need to replace it with 1. So like that we need to choose the bookkeeping mechanism for keeping the track of progress of algorithms. So these are the important things we need to implement. We need to focus on for implementing the algorithm in the Turing machine. And the Turing machine allows to design on algorithm without reference to the machine. So here, without reference to the machine, we can design an algorithm. So there is no dependency on the machine. So here we will generally define the algorithm. We are not dependent on any machine. And by saying that Turing machine is a general model of computation. So with this, all the statements, we can say that this is a Turing machine is a general model of a general model of computation. So Turing machine is a general model of computation. So that is nothing but any algorithm procedure that can be carried out can be carried out by the Turing machine also. So generally, so whatever there for the carried out procedure, algorithmic procedure will what we will do. So those all procedures will be also done by the Turing machine. So here, this church first formulated the above statement. So who proposed this statement, in the sense Alan Turing. So here This is about the Church-Turing Thesis. And here let me summarize all the statements. So what are the statements till now we discussed? Though all the steps that are crucial to human computation can be carried out by the Turing machine. So here with the statements previously we just talked about the general purpose of computation. General model of computation is a Turing machine. So all the steps that are crucial to human computation. So like iterations, so many additions, so many multiplications, so many subtraction kind of functions if we want to compute at a time, we the human for human it is like burden. So for that case we are, it is crucial to human computation, so it can be carried out by it. In that case we are using this Turing machine. So these digital computers which are based on this Turing machine. So here whatever their computer science. So we can, by this statement we can say that the Alan Turing, which is who is the father of computer science, and various Turing machines are there have been suggested in the Turing machine to make general purpose computer. So based on the variations, so based on the situations we can create, we have many variations in the Turing machine that are which are useful for the computer. So general purpose useful for the computer. So based on the computers, we are using the variations in the Turing machine. So other theoretical models of computation like UTM. So what is this UTM? In the sense Universal Turing Machine. So Universal UTM. Universal Turing Machine. So universal Turing machine have been proposed. So for maintaining the other theoretical model of computation, so here there are some other models of computation are there. So for that one we will like to describe about universal Turing machines have been proposed. No example of any algorithmic procedure. So here there is no kind of particular algorithm for the Turing machine. So based on the functions, based on the language acceptance, the logic behind the Turing machine is there. There is no algorithmic procedure is there, not be implemented on Turing machine. No precise proof or explanation can be given for Church-Turing thesis. So for this theories, there is no particular proof to declare the statement. So by saying the generalized statement that Turing machine can do anything, so anything that is nothing but a model for the computation. So this is about the Church-Turing thesis. And next, recursive languages. So what is meant by recursive language? So here the language L is recursive, so which are decidable. So we have two types of things languages. One is decidable language and decidable language. And here if we are talking about the recursive languages, so those are all called as decidable languages. The recursive which represents the decidable language. So a language L is recursive if L is the set of strings accepted by some Turing machine that halts on every input. So suppose here we are talking about the decidable language that is nothing but recursive language. So that while implementing the recursive languages, so we have a set of strings. So in that one we have a set of strings, so like these are examples. So for this accepting for this string accepted by some Turing machine, so this language which is accepted by Turing machine that halts in the sense that will accept on every input. So every input what we are giving as an input, for every input it is halting. So for every input string it is halting. So that is nothing but a recursive decidable language. And here when coming to the example, when a Turing machine reaches a final state, it halts. And we can also say that Turing machine M halts. So with the statement where whenever the Turing machine which is reaching the final state, we can just say that it is the Turing machine is accepted. So, and whenever M reaches the state Q, so instead of accept state, the Turing machine, let me write. So if it is accepted, so when a Turing machine is reaching the accepted, it halts. And the QM machine reaches a state Q and a current symbol A to be scanned, so that this entire thing is represented as transition of Q comma A is undefined. So this Turing machine which is not going to the accepted state and it is going to the other state which is undefined. So in that case, so there are two types of machines we discussed. So one is accepted and one is not accepted. So there are Turing machines that are never halts on some input. So here this is never halting. For the A input, the Turing machine is not halting in that language. So this input is not satisfied. So for this some inputs, if any one of these ways, so we make the distinction between the language accepted by the Turing machine. So in that cases, so here the input whatever we are giving, that is accepted by the Turing machine. For some inputs, this Turing machine which we constructed is not accepting the input. So we divided into two things, two Turing machines. One is accepted and one is not accepted. That what we are. The statement says that the Turing machine which the string, or for all the string it is accepting, and for this in some input string it is not, never halting. That is nothing but never accepting. So this is about the recursive languages and the language recursive enumerable language. So recursively enumerable language which is L, and if L is a set of strings accepted by some Turing machine. So the language which is not accepted by all the Turing machine, only some Turing machine this L is accepting. So here if L is a recursive enumerable language, then L, if W, the W is nothing but word which is belongs to language. The W which is nothing but a string, which is W is nothing but a string which is accepted by the language, then Turing machine halts on the final state. So then the Turing machine will halt on the final state. So that is nothing but it is accepted by the Turing machine. And W which is not the string which is not belongs to the language. So the input what we are giving is not belongs to that language. The Turing machine halts on non-final state or loop forever. So loop forever. So here it is not accepting state, non-final state. So non-final state it is reaching or loop. So there may be a continuous loop. So this is about the recursive enumerable language and recursive language. So recursive languages, so what we discussed, we have two types of languages we have. So what languages are there, right? So for some languages, only some Turing machine will halt, and so for some languages only the Turing machines which are not in the accepted state. So we divided the Turing machine into two things. So the deviation which is shown here, if L is a recursive language, then W belongs to L, so word which is belongs to L, then Turing machine halts on a final state. And here W which is not belongs to that language, TM halts on non-final state. So which is not non-final state. So here when compared with the two languages, we have two languages. One is recursive enumerable language and recursive language. So recursive language which says that which is not the W which is not belongs to that language, it will be on the non-final state, which is not on the final state. And when compared with the enumerable language, which is in the non-final state or loops forever. So this enumerable and language, normal language. So recursive enumerable language and normal recursive language, which is a different here, while which is not belongs to the language, the W which is not belongs to the language, it will be halt in a it is on the non-final state or forever loop, and this is in the enumerable language. And in the not recursive language, so it should be halts in a non-final state. Instead of final state, it is not there in the, it is in the non-final state. So, and recursive languages are also recursive enumerable. So, recursive languages. So, these languages is also recursive enumerable languages. So, proof what is that? If L is a recursive, then M is a Turing. Then there is a Turing machine which decide the member in language. So, here we are proving that L is a recursive. So recursive, which is nothing but decidable. So decidable language. So this, if L is a decidable language, then there is a Turing machine which decide member in the language. So member, which is represented as M here, and this member in the language, then M accepts L X if X is the language, if X is in the language L. So a member M which accepts X which belongs to the language. So X which belongs to the language, and M results on X if X is not in the language L. So here it M results X which is not belongs to the language. So according to the definition, M can recognize the strings in language. So this machine M which recognizes the member in the language, which is recognizes the string in the language. So which is strings in language, they are accepted by those strings. So here the M machine which are the language which whatever the strings which are belongs to, which are strings which are belongs to the language only accepting. So this statement says that the recursive languages are also recursive enumerable languages. So this is about the recursive enumerable language, and these are the references. So in the coming video, we will discuss about the Turing machine types. So how many types of Turing machines we have? So we will discuss that one in the next video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.